Hello and welcome. In this lecture, we will be discussing about inorganic polymers, to be specific with silicates as inorganic polymers. 95% of the Earth's crust consists of silicate minerals, aluminosilicate drugs and silica. During the cooling of Earth, since silicates were lighter, so they crystallized and floated on the top, accounting for the higher concentration of silicates in the Earth's crust, which can be seen in the adjoining figure what is the ratio of various minerals in the Earth's crust and on the surface. There is a Bowen series for mineral layers which tells us the arrangement of various minerals in the Earth's crust. The topmost mineral is by the name olivine, followed by pyroxene, biotite mica, orthoclase feldspars, muscovite mica, quartz and zeolites. This is the way in which the minerals are arranged or exist in the Earth's crust. The simplest and lightest minerals are formed in the top layer. All silicate formulae are idealized because it is not possible to represent them by a single formula. When we talk about the very first mineral, which is olivine, the general formula is either magnesium silicate or iron silicate, and the adjoining figure shows us the picture of olivines. However, when very little iron is present, then it is written as magnesium silicate, or the mineral is named as forsterite. When very little magnesium is present, then it is written as ferrosilicate or fryolite. Thus, olivines are those minerals where there are varying quantities of magnesium and iron almost equal in proportion. The industrial preparation method of silicates includes: they can be prepared from sodium carbonate in the following manner. Sodium carbonate at a treatment of 1400 degrees centigrade releases carbon dioxide, which on treatment with silica produces sodium silicate. As a result of this, a glassy substance which is obtained as by the name sodium silicate is a water soluble glass which gets dissolved in hot water under pressure and is then filtered. Similarly, alkali silicates are those silicates with alkali metals in the melt. They are used in liquid detergents to keep the pH of the detergents high. However, they cannot be used with hard water because insoluble calcium silicate will precipitate out. So, these alkali silicates wherein calcium is used as an alkali metal, taken as an alkali metal in liquid detergent, cannot be used with hard water. Sodium silicate is used as an adhesive for paper, cardboard, etc. Sodium silicate is another alkali silicate. It is also used for roofing tiles, putty and for making silica gel. Putty is the adhesive which is applied to join or as a fevicol for various purposes in housing. Another example of silicates is granite, which is used in building materials. Bricks and cement are also made of silicate apart from ceramics and glass. The picture which shows a slab of granite which is used generally to make kitchen tops and kitchen tables. Coming to the structure of silicates, the basic unit in silicates is SiO4 tetrahedron, which is shown in the adjoining figure. In all type of silicates, SiO4 tetrahedra share corners, that is oxygen atoms, but never their edges or faces to form chains, double chains, sheets, etc. The sharing of oxygen atoms through corners is shown in the figure below. The silicate ions are packed in different ways, creating octahedral or tetrahedral holes which are occupied by metal ions. So when the silicate ions join to each other, they create holes in between them, because the SiO4 tetrahedra, which joins with corners as can be seen in the figure, leaves spaces in between, and these spaces are occupied by metal ions, as in case of alkali metal silicates. Metal ions can fit into either kind of holes, that is either octahedral holes or tetrahedral holes, if they have the similar radii. That means for a metal ion to fit the hole of a silicate unit, silicate tetrahedra, the metal ion needs to have a similar radii so that it can go in that hole. They can also replace each other in the same class of minerals, which is termed as isomorphous replacement, that is replacement without changing the structure. A very good example of isomorphous replacement are aluminosilicate minerals. Aluminosilicate minerals arise when aluminium replaces silicon in the SiO4 tetrahedra, since it can fit into both tetrahedral and octahedral holes. The approximate size of silicon and aluminium is the same, so it can easily replace silicon in the silicate tetrahedra, and that kind of replacement is termed as isomorphous replacement, because the structure which is resulting is similar to the original structure, only the ion, the metal ion changes. Various kinds of silicates which we will be discussing now. In the first type are orthosilicates, which are also called nesosilicates. They are those silicates which contain discrete SiO4 tetrahedra. By the meaning of discrete SiO4 tetrahedra means that they are singly present, and this SiO4 tetrahedra are not joined to each other by oxygen or any other way by corners. So they are present singly, and this is the way in which we show in the figure the SiO4 tetrahedra, the bond angle between SiO and the bond length which is shown as between Si and O. Zirconium silicate or zirconium orthosilicate, as we call it, is a type of an orthosilicate which is used after polishing in place of diamond in jewelry, as we know as artificial diamond or zircon. But since zirconium is very soft, so the cut edges lose their shine and sharpness after some time, and as we know, the artificial jewelry, or as we say the zircon jewelry, becomes dull after repeated uses or after some time, because the edges are very soft and they lose their shine, which is unlike diamond, which retains its shine forever. Another class of silicates is pyrosilicates, or also called sorosilicates. They have two tetrahedra sharing one corner. These type of silicates are comparatively rare, and as can be seen in the figure, the silicate tetrahedra are joined to each other with the help of one oxygen, which is common between the two SiO4 tetrahedra, and the joining is through the corners, as we have already seen and discussed that the silicate tetrahedra in any kind of polymers are joined through only corners and never through edges or faces. In the figure, the red balls represent oxygen, and the blue balls, two blue balls which are being seen in the center of the tetrahedra, represent silicon. An example of pyrosilicate is thorvitite, which is a scandium silicate mineral. Another type of silicate is cyclic silicates, also called as ring silicates. These have tetrahedral units joined into rings, which can be seen in the figure. There are three tetrahedral SiO4 units joined together to form a ring, and again the sharing is through oxygen atoms, the corners of the tetrahedra. And the example of cyclic silicates which is there is wollastonite, which is a calcium silicate mineral. Another example of cyclic silicates or ring silicates is beryl. Beryl is a pale green colored semi-precious stone which has the composition Be3Al2Si6O18. The first figure which is shown below is of beryl. Emerald is a precious stone, we all know that. It has a similar composition, but 2% aluminium is replaced by chromium in emerald. That means the formula of emerald and beryl is the same, only the difference is that instead of aluminium or 2% aluminium, chromium is present, and therefore it causes a slight change in the color of the semi-precious stone, which is shown in the second figure. So emerald is bright green towards the dark side green color, whereas beryl is a light green color semi-precious stone. When we talk about chain silicates, SiO4 tetrahedra are linked in different ways and they give rise to single or double chains. Different structures exist for chain silicates. Generally, asbestos minerals exist as double chain structures, which can be seen in the figure that there are two chains which are linked to each other, wherein there is a sharing of oxygen between the upper layer and the below layer to form a sheet or a double chain silicate, as to say. Coming to sheet silicates, another type of silicates or polymers which exist. These are all inorganic polymers as we are discussing. Sheet silicates incorporate the double chain basic structure into sheets extending in two dimensions. Single chain structures are termed as pyroxenes. That means if we talk about silicates, the single chain, if we take figure and the top layer which if we consider, then that is a single chain silicate which is called pyroxene, and the general formula for pyroxenes is SiO3N2N-. For example, lithium aluminium silicate, which is a major source of lithium, is a sheet silicate or a single layer silicate. Double chain structures are termed as amphiboles. That is the structure we have just seen. This is a double chain structure and this is termed as amphiboles. The general formula for amphiboles is SiO4O11N6N-, and the best example for amphiboles are asbestos, and therefore these are also called asbestos minerals. These are all fibrous minerals because it is possible to cleave these minerals into fibers, and this cleavage takes place through the oxygen atom, that is the place where the two silicates or line silicates are joined to each other. So they cleave parallel to the chains because chains are held together by weak forces, and as we have seen in the structure, there are two chains joined to each other and these two chains are held together by weak van der Waals forces. So their cleavage can take place through this parallel to each chain, and therefore sheets can be made from such kind of silicates. Within the chain there are SiO bonds, that means bonds between silicon and oxygen, which are very strong. Each mineral has a typical cleavage angle which identifies the mineral. That means for each mineral the angle of cleavage is different. Asbestos minerals are of commercial importance. The fibers can be woven into fabric for fire retardant suits for firemen and the military. That means asbestos minerals can be made into clothes or suits which are resistant to fire and used by firemen. They are also used for roofing sheets, and because of its acid and alkali resistant properties, asbestos sheets are used in laboratory tables. However, asbestos dust can cause scarring of the lungs and even lung cancer in miners, that means people who are working in the mines, and labor working in the asbestos industry. The use of asbestos is thus being minimized, and wherever possible, asbestos is handled in wet to reduce the dust, and miners and workers are required to wear masks so that the dust does not enter their system and does not injure their lungs too much. The asbestos is to be handled in wet, meaning that it is first sprinkled with water so that the flying dust settles down and does not enter the system of the people who are working with it. White asbestos is also a type of sheet silicate having the formula Si2O5N2N-. The simplest sheet silicates are planar in structure. This is a figure which is showing asbestos dust and the main requirements, that is a mask and the protective glasses for miners and the laborers who are working in asbestos industries. Most sheet silicates have a complex sheet structure with layered sheets having 2 or 3 layers. Silicate layer alternating with hydroxide layer. That means in case of sheet silicates, one of the layers is that of SiO4 tetrahedra and the second layer is that of OH minus or hydroxide ions. For example, if we consider magnesium hydroxide, which is brucite, a layer of magnesium hydroxide is followed by a silicate layer or aluminium hydroxide, which is called gibbsite layer, followed by a silicate layer. So, one silicate layer alternating with one hydroxide layer, that may be in the form of brucite or gibbsite. The layered sheets are stacked parallel to each other, giving the mineral, and the adjoining figure shows us brucite and gibbsite layers or sheet silicates wherein silicates and hydroxides are interlinked. Other examples of sheet silicates are kaolinite, which is an aluminium hydroxide silicate mineral, white asbestos or magnesium hydroxide silicate mineral. In this, as we say, one silicate layer is there and one hydroxide layer is there. And third one, which is talc, which is a magnesium hydroxide silicate layer of a different composition. Kaolin is a high grade kaolinite mineral called China clay. The best quality of kaolin is of Cornwall in England. These can be shaped into objects in cold and then fired in furnaces. Firing fuses the sheets together, making the mineral hard. That means the China clay we talk about, or the kaolin material with the help of which various ceramics are made, are actually sheet silicates or kaolin. Ceramics are made by firing the molded shapes. Firing means subjecting the molded shapes to fire so that the sheets get fused and harden the material. Glaze is the shine which is put on the pottery by dipping the pottery in a solution of heavy metal oxide like SnO2, which is stannous oxide, and lead oxide, which is PbO2, before firing or before subjecting the ceramics to fire, before subjecting the pottery to fire. Pigments to make the pottery colored can be used to the pottery either before glazing or in case of fine pottery, after one glaze and firing, the pigment is applied and the firing is done a second time. Talc, which is also an example of sheet silicate, has a number of uses. Talc is also called soapstone. It can be ground into very fine powder because the forces which are holding these sheet silicates in case of talc are very weak. So, they can be ground into very fine powders, they can break easily. It is a very soft mineral, that is talc is a very soft mineral, and it is lowest on the Mohs scale of hardness. When we talk about Mohs scale of hardness, it is a scale which is telling the hardness of a particular mineral, and when we say that talc is lowest on the Mohs scale, that means it is the most soft mineral in terms of silicate polymers which is known. Talc mineral is thus used as talcum powder in cosmetics to give that slippery and dry feeling, and because of its slippery or soapy feeling, it is also used as a dry lubricant. Hence, clay minerals like kaolinite, talc and Montmorillonites have a wide range of uses. Kaolinite and talc we have already discussed. The third type of new clay mineral which we are seeing is Montmorillonites. They have thixotropic properties, that is, their viscosity changes on agitation. Aluminosilicates are an example of Montmorillonites. So, as the solutions of Montmorillonites are stirred vigorously, then the viscosity can either decrease or it can increase depending upon the Montmorillonite. When some of the silicon is replaced in the tetrahedral holes by aluminium, cations are introduced to balance the charge. Montmorillonites, thus, when we have in the previous slide just discussed that Montmorillonites are aluminosilicates. Aluminosilicates are those minerals where some of the silicates or some of the silicon atoms are replaced by aluminium. So, Montmorillonites have negatively charged layers with cations between them. When this is broken, the surface is negatively charged and the edges are positively charged. These arrange themselves in such a manner, that is plus minus in rows due to electrostatic attraction and forms a semi-solid gel. On stirring, this kind of a regular arrangement of plus and minus ions or cations and anions, this arrangement is broken and the viscosity of the Montmorillonites is lowered. Hence, it becomes watery. Thus, it is used in thixotropic non-drip emulsion paints. When we talk about paints, then paints are those which are applied on generally furniture or doors, etc. When the paints are being applied, then it is observed that these paints, with the help of a brush, they do not drip down. Although they are liquid, they do not drip down, do not fall down. Instead, they are slightly viscous, but they are also watery, which enables the paints to be applied on the furniture or the doors. So, hence, they are actually thixotropic molecules or Montmorillonites, which can be seen in the adjoining figure also, which are important in paints because they are having thixotropic properties. So, this is the figure which is showing the rock as a Montmorillonite, and the adjoining figure which is showing paints which are having thixotropic properties, and the major constituents of paints which are applied on doors and windows and furniture is Montmorillonites. Thank you.